equal to P naught times exponential of e to the power minus z by h. Okay, where admit someone is trying to enter the class. Admit. Okay, all right. So who is that? Bijit Kumar. Bijit, are you there? You have just joined, right? Bijit?
Yes, sir. Yes, sir.
Yeah, can you switch on your video? Can I see you?
Yes. So are you seeing me?
Not yet. Not yet. Yes, now I can see you. Yes, good. Okay, all right. So while I am presenting the PowerPoint, are you able to see me?
Yes, sir.
All of you are able to see me while I am presenting the PowerPoint?
Yes, sir.
Yes, sir.
Yes,
Okay.
sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
Okay, good. Very good, very good. Yeah, you have to be very, very responsive, okay, and interactive, so that I know that I am online. Otherwise, I may get disconnected sometimes, and I may not know that. All right. So the pressure, as I said, and density both decrease exponentially with height, and it is given approximately by this relation: P is equal to approximately P naught times exponential of minus z divided by h. Okay, where this P naught is a pressure at a reference level, usually taken at the surface, okay, Earth surface. Z is at any height z, and h is so-called the scale height. H is the scale height. Have you heard about the scale height? Have you heard about the scale height? Devasis?
No, sir.
No,
No,
sir.
sir. Okay.
Yes, sir.
Okay. Have you heard about the scale height? No?
Yes, sir.
Okay. So what is a scale height? Can you define a scale height?
S- Sir, it is the means it is the factor with which the height decreases exponentially.
No, not correct. Not correct. Anyway, so we shall discuss it here today. Okay,
Sir.
and also subsequently also in other classes we shall discuss about this. I said h is the scale height. Okay, this is the E folding depth referred to as the scale height, and P naught is the pressure at the some reference level considered as the surface at z is equal to 0. Okay, the scale height is the vertical distance over which the density and the pressure fall by a factor of 1 by E. Okay, where E is equal to say 2.7, so approximately 35% of the value at the sea level. That means the scale height is the height above the ground where the value of density and pressure falls to about 35% of the sea level value. Okay, we shall discuss more in detail about this scale height in maybe in the next classes. But for now, this is the definition of a scale height that you can remember. Okay, scale height is the vertical distance over which the density and the pressure fall by a factor of 1 by E. That is approximately 35% of the value of sea level. Okay. In the lowest 100 kilometers of the atmosphere, the scale height ranges roughly from 7 to 8 kilometer. Okay, that means it remains almost the same. The scale height of the atmosphere is almost the same till 100 kilometer altitude, and the value of the scale height is about 7 to 8 kilometer. Okay, now if we divide this equation by P naught and take natural algorithm, okay, then we get log of P by P naught is approximately equal to minus z divided by h. Okay, what we did, we divided this equation by P naught and took the natural algorithms. Okay, and we obtained this relation, log of P by P naught equal to minus z by h. This relationship is useful for estimating the height of various pressure levels in the Earth atmosphere. So if you have to calculate the height of various pressure levels, then you can calculate that from this relationship. Okay, you know, pressure decreases with height, right? What is the typical pressure at the sea level, at the Earth's surface? What is the typical pressure? Normal pressure? Who will say?
1013 bar.
Yes, approximately 1013 hectopascal or millibar, right?
Millibar.
Millibar, hectopascal are the same thing. Okay, so approximately the mean sea level pressure is 1013 hectopascal or millibar, and but it can vary from place to place, right? It can vary from place to place, and it can also vary with time, right? It can vary with time because when there is a passage of any system, like say tropical cyclone or western disturbance, then pressure will drop, right? Besides, there is also a diurnal variation of the surface pressure. There is a diurnal variation of the surface pressure. If you plot the value of pressure at the surface for 24 hours, hourly value of surface pressure, if you plot on a graph, you will find that there are two maxima and two minima. Okay, you'll find that there are two maxima and two minima. Okay, and the two maxima are generally at 4 o'clock in the afternoon and 4 o'clock in the morning, and two minima are 8 o'clock in the morning, 8 o'clock in the evening. Right. So this is the diurnal variation of the pressure. So the sea level pressure, normal standard sea level pressure is 1013 millibar, but it can vary with place, and it can also vary with time. Okay. So we can estimate the pressure. Similarly, as you go upwards vertically in the atmosphere, since it is say approximately 1000 millibar or 1030 millibar at the surface, as you go up, there will be pressure. Say you will encounter pressure at some hill station. Suppose if you are standing over a hill station, over a hill mountain top. Okay, let us say you are standing over, say, there are many places, where you have the hill stations like Kodaikanal in the south. Kodaikanal, there is a mountain station, right? I mean hill station. If you go to Simla in the north, Himachal Pradesh, Simla, right? If you go to Mussoorie in the north, or any hill station for that matter, because of the height of the mountain or height of the hill, the surface pressure will be less there, right? Let us say, depending upon what is the height of the mountain or the hill station, the surface pressure can be 900 millibar or say 850 millibar and so on, right? As you go up, generally, at the tropopause level, the pressure is approximately 100 millibar, right? At the tropopause, the tropopause, the top of the troposphere is about 100 millibar, but it can vary from place to place. Like tropopause is at a lower altitude in the polar region, but it is at a higher altitude in the equatorial region. Height of the tropopause will vary according to place, right? So the pressure at the tropopause is approximately 100 millibar. Similarly, say middle of the atmosphere we generally consider to be 500 millibar. Middle of the atmosphere is approximately 500 millibar. And say, for example, if you are at the Tibetan plateau, right, or the Mount Everest, what is the height of the Mount Everest?
Sir, 8,400.
8,848 meters.
Approximately, say 8 kilometers above the mean sea level, right? So the pressure at the Mount Everest will be much less, maybe about 250 millibar or 300 millibar. No, more than 300 millibar is approximately 9 kilometers. So it will be 350 millibar at the top of the Mount Everest. But average height, say, of the Tibetan Plateau is considered a very high elevated region over the Earth's surface. The average height of the Tibetan Plateau is considered to be about 5 kilometers, 500 millibar roughly. Okay, so in the atmosphere, as the pressure decreases with height, we can imagine now the surface of equal pressure called the isobaric levels, right? The surface of equal pressure is called isobar, right? Iso lines means line of equal values. Isobars means the line of equal pressure. So isobar, 500 millibar isobaric surface, or say 200 millibar isobaric surface. So when an aircraft is flying, typical altitude of the aircraft, when it is at the highest level, what is the height of the aircraft? Do you know? Any idea?
So 35,000 feet.
50,000 feet.
50,000 feet.
What is saying 50,000 feet? 50,000 feet is quite high. Generally, it is within the troposphere. Okay. It is within, actually less below the tropopause generally. Normal height when it is cruising at the top, speed. Generally, what is the cruising speed of the Airbus? You know, the cruising.
Sir, 800 kilometers per hour.
Yeah, approximately 700 to 800 kilometers. So at that speed, its height is about 30,000 feet, approximately 30,000 feet. That means 1/3 of that, you can say kilometer, about 10 kilometers, right? So the altitude of the aircraft where it is cruising at the highest speed, 700 to 800 kilometers per hour, is about 30,000 feet, sometimes above, sometimes below, right? Roughly about 10 kilometers. So the pressure at the 10 kilometer height is roughly about 250 millibar. Of course, inside the cabin, the pressure is maintained. Otherwise, the aircraft will blow, right? So inside the cabin, pressure is normal pressure that we expect at the Earth's surface, right? But if you go outside when it is flying at the highest level, the pressure will be about 250 or 300 millibar. How do we calculate at what level the pressure is, at what height the pressure is, how much? That is using something like this relationship, okay? The isobaric surface, height of the isobaric surface, you can calculate from this relationship, or pressure at any altitude. Let us say we want to calculate the pressure at 10 kilometer height above the Earth's surface. We can use this relationship to calculate the pressure, okay? Then let's say temperature, how the temperature varies. Now, the temperature also vary according to the height, right? And as you know, many of you might have studied already the vertical stratification or different layers of the atmosphere, right? The atmosphere is divided into basically 4 layers. Most of you should know, maybe knowing that. One is the troposphere, the lowest one, then the stratosphere, then mesosphere, and the thermosphere, right? Have you heard about these things studied earlier? Yes or no? Yes, sir.
Yes, sir.
Good. Yeah, good. So this is how it looks like the vertical structure of the atmosphere looks like this. This diagram should be familiar to all of you, I hope. So here the lowest layer is the troposphere, although it is showing about 10 kilometer, 11 kilometer, but depends upon where, right? Depends upon where. 10, 11 kilometer may be about mid latitude, but in our latitude, we are in the tropics, right? We are in the tropics. So in the tropics, tropopause is further high. Now it can be about 15, 16 kilometer above the mean sea level, the height of the tropopause. Okay. The interface between troposphere and the stratosphere is the tropopause. Okay. So above troposphere is the stratosphere, right? And the height of the stratosphere is approximately up to about 50 kilometer or so. So again, the interface between the stratosphere and mesosphere is called the stratopause. So then there is a mesosphere which extends up to about 80 kilometer, right? And this interface between mesosphere and thermosphere is approximately, is called mesopause, and then above that is thermosphere, okay, about 100 kilometer. So these are the different major layers in the atmosphere, right? Major layers in the atmosphere. And as you can see that this is the profile of the temperature. This is the profile of the temperature, how the temperature varies with height in different layers of the atmosphere. So the troposphere is marked by a generally decreasing temperature with height. Okay, temperature is decreasing sharply with height at an average rate of about 6.5 degrees centigrade per kilometer. Okay, this is called the lapse rate. We call the lapse rate of the atmosphere, 6.5 degree centigrade per kilometer. If you go up, you will lose the temperature approximately at the rate of 6.5 kilometer. Okay, per kilometer, 6.5 degree per kilometer, denoted by gamma. Gamma is the lapse rate here, is equal to approximately del T by del Z. That means rate of change of temperature with height is approximately equal to 6.5 degrees centigrade per kilometer. Okay. Now this lapse rate is supposed to be the normal lapse rate of the atmosphere, but it can change, right? It can change according to the situation, right? According to the water content in the atmosphere. According to the water content in the atmosphere. Last time we were talking about the water cycle, right? Water cycle, I mean hydrological cycle rather, not water cycle. Somebody said, should we call it water cycle? Actually, it is not a water cycle, but it is a hydrological cycle because water can exist not only in the liquid form, but it can exist also in the gas form, right? It can also exist in the frozen form. So therefore, it is not appropriate to call it water cycle. I think Sri Lakshmi, you had mentioned this, right? This question. Sri Lakshmi, can you hear me?
Yes, sir.
Yeah, right. You said, yeah, whether we should call it water cycle. It's not appropriate to call it water cycle because water is not the form in which it exists
Sir, I
always
can't
in the
hear you.
atmosphere, right? So we better call it hydrological cycle because it can exist in water vapor form, or solid form, etc. Right? So depending upon the water vapor content or moisture content of the atmosphere, the lapse rate can be different. Right? Suppose if the atmosphere is dry, so if the atmosphere is dry, then the lapse rate is larger, higher. You will lose the temperature at a higher rate, and that's called the. Suppose if it is dry, then we call it dry adiabatic lapse rate. We call it dry adiabatic lapse rate. Have you heard about this dry adiabatic lapse rate?
No,
No,
sir.
sir.
No.
Yes, sir.
Okay. Yes. Okay. Somebody yes. Somebody no. What is the dry adiabatic lapse rate? Devasis? How much is the dry adiabatic lapse rate?
Sir, I have read about it. I just don't
Okay.
remember.
Okay.
Sir, I
Yeah.
have read about it. I don't remember it exactly.
Okay, okay, fine. So now you can remember the dry adiabatic lapse rate is approximately 9.8 or 10 degrees centigrade per kilometer. 10 degrees centigrade per kilometer. That means the atmosphere is dry,
Yes,
the
sir.
temperature will decrease more rapidly. Okay. And when it is saturated, moist, saturated, then the lapse rate is less. It will lose the temperature at a lower rate. And that is called the saturated adiabatic lapse rate. Saturated adiabatic lapse rate, that is approximately about 4 degrees centigrade per kilometer. Okay. The saturated adiabatic lapse rate is about 4 degrees centigrade per kilometer. The dry adiabatic lapse rate is about 10 degrees centigrade per kilometer. And this is supposed to be the normal lapse rate,
Sir.
which is about 6.5 degrees centigrade per kilometer.
Sir,
Somebody is
sir.
asking something? Yeah.
Yes, sir. Sir, the this this saturated adiabatic lapse rate is also called wet adiabatic lapse rate.
Standard terminology is the saturated adiabatic lapse rate. Wet bulb temperature is there. There is a wet bulb temperature definition, but that is a different thing. We shall talk about that later on. Okay, but normally it is referred to as saturated adiabatic lapse rate or moist adiabatic lapse rate, also called the
Yes, sir.
moist.
This moist or wet adiabatic lapse rate.
Yeah, moist adiabatic lapse rate. Generally, more conventionally or more popularly called moist adiabatic lapse rate. Okay,
Yes, sir.
moist adiabatic lapse rate. Okay, and moist adiabatic lapse rate is less, about 4 degrees centigrade per kilometer. The dry adiabatic lapse rate is about 10 degrees centigrade per kilometer, but 6.5 is the normal lapse rate. Okay, so in the troposphere, normally the temperature decreases at this rate, But sometimes in some thin layer of the atmosphere, in the lower level, very thin layer of the troposphere, the atmosphere will have a increase of the temperature with height. In the very thin layer of the atmosphere, depending upon situation, sometimes temperature can increase as you go up, and that is called the inversion. That is that kind of layer where the temperature increases with height. We call the inversion layer, right? Inversion layer, and that occurs generally in the winter season. Approximately, it occurs in the winter season generally. Okay, the inversion can occur both at this ground, at the surface, as well as in the layer above the surface also. And actually, that is one of the very important things for the formation of fog. The existence or presence of inversion is very, very important for the presence of the fog, occurrence of the fog, right? So, as you can see that, above the troposphere, in the stratosphere, the temperature starts increasing, right? So that means you can say there is an inversion, a big inversion layer. The entire stratosphere, also called the ozonosphere, because the ozone is supposed to be maximum in this layer, stratosphere. So there is a temperature inversion, and when there is a temperature inversion, actually we'll discuss about this, in the class. It does not allow the convection to penetrate, to go up. No. So the clouds generally will not go above tropopause because of the presence of the strong inversion in the stratosphere. The top of the cloud, the deepest cloud, will go normally up to tropopause. Sometimes, in some cases, when there is very strong upward motion of draft in the cloud, like a deep cumulonimbus cloud, then its top can shoot or overshoot the tropopause, but normally it does not. It remains below the tropopause. Okay, the top of the cloud. So in this case, T is the temperature, gamma is the lapse rate. Tropospheric air accounts for about 80% of the mass of the atmosphere. That means maximum mass of the atmosphere is confined within this layer only. Within this layer only. Okay, tropopause. 80% of the total mass of the atmosphere. Okay. It is relatively well mixed and continually cleansed or scavenged of aerosols by cloud droplets and ice particles in the form of rain or snow. Okay. This tropopause is well mixed because of the existence of the convection. Okay, existence of the strong convective motions, rising motion, sinking motion, upward motion, downward motion, updrafts, downdrafts, etc. Okay, thermals. So it's a very well mixed troposphere. Okay, and also it is cleansed regularly because of the rainfall. As the rainfall occurs, as the precipitation occurs, it cleans the atmosphere. So it scavenges the aerosols out of the troposphere. Okay. Embedded within the troposphere are thin layers in which temperature increases with height. It is called the temperature inversion. We just talked about that earlier. Sometimes there can be temperature inversion. If you just plot the temperature profile observed by radiosonde. Radiosonde, have you heard of the radiosonde? Have you heard about the radiosonde? No? Okay, radiosonde is a instrument which we tie in a balloon, and fill up the balloon with hydrogen and just lift the balloon. So the balloon will rise because hydrogen is lighter than the air. So as it goes up, it will measure the profiles of temperature, humidity, and wind fill, and we have a receiver at the ground. So we keep receiving the temperature, humidity, and wind speed, wind direction, etc. at the surface as the balloon rises up. As it goes up, the balloon will start expanding because the pressure decreases as you go up. So by the time it reaches about the tropopause, or sometimes it can exceed the tropopause in some cases, the balloon quality is very good. If the quality of the rubber is good, then it can go up to about 30 kilometer, 35 kilometer also. And that's how we measure the profiles of the temperature and moisture and wind speed and wind direction every day, right? Every day the profile of the temperature, humidity, wind speed, wind direction we measure in the atmosphere by launching this reduction balloon. And that is done, by whom? Who does this job regularly? Who takes this observation regularly? Whose responsibility is this to take the observations regularly? No?
Meteorologists.
Yeah, India Met Department. The India Meteorological Department of Bharat Mausam Vigyan Vibhag is the responsibility of taking all meteorological observations throughout India. And similarly, all the countries in the world, right? You have heard about the WMO, the World Meteorological Organization.
Yes, sir.
Yeah, the part of the United Nations, UN, right? WMO is a part of the UN. And according to the WMO's convention, all the countries in the world must have a meteorological department whose responsibility is to collect meteorological observations at regular interval of time, okay, throughout the day, every day, round the clock, round the year, okay. So IMD takes the observation every day, generally twice a day, and we have about 40 radio sound stations all over India. All over India, we have about 40 radio sound stations. Normally, it's supposed to be launched twice a day, one at 00 UTC in the morning and one is at 12 UTC in the afternoon. So UTC, GMT, Greenwich Mean Time, right? So what is the difference between Greenwich Mean Time and IST, Indian Standard Time?
So GMT is the standard which we follow. So GMT is at 0 degree longitude. IST
Huh.
is specific for India.
Yeah. So how much is the time difference between GMT and Indian time?
5.5 hours. Sir.
Right. Correct. Very good. So 00 UTC means 5:30 in the morning, right? In India. So at 5:30 in the morning in India and 12 UTC, that means 5:30 in the afternoon in India, right? So we collect the observations of the atmosphere, the vertical profiles of the atmosphere at twice a day, one in the morning at 00 GMT and one in the afternoon at 12 GMT, right? 5:30 in the morning, 5:30 in the evening. Same convention is followed all over the country. I mean, not only all over the country, but all over the world. All countries of the world are supposed to launch radio sound. One in the morning at 5:30 and other in the afternoon in the 5:30 in the afternoon. Right? But because the radio sound, when we tie the instrument in the balloon, it's quite an expensive instrument. So once the balloon bursts, after it reaches the tropopause, then the instrument is lost, it falls somewhere. And so we lose the instrument, and the instrument costs roughly about 10 to 15,000 rupees. Okay, so every time we launch the balloon, we lose 10 to 15,000 rupees. So that means if we launch twice a day, that means 30,000 rupees per day we lose, right? And therefore it is quite expensive. So as a result, not all the stations launch the balloon 2 times. They launch generally only once a day because it's quite expensive, right? So they just launch only once a day. And normally at 12 UTC in the afternoon. Okay, sometimes also if the station is very important stations, like main meteorological centers, New Delhi, Chennai, etc., Mumbai, Calcutta, maybe twice a day, but rest of the stations they take just once a day. Okay, and many countries, because it's so expensive, many countries don't even have radio sound because of that expensive, right? So of course that is the manual observations we collect of the vertical profile of the atmosphere, of the troposphere, every day, right? But then nowadays we have got the satellites, right? So satellites can also sense the profiles of the temperature, moisture, etc., and the wind also. But then ground instrument is a ground instrument, right? What is gone into the space, generally we believe that they are fine because they are well tested in the laboratory before they are launched. But still, we don't know how long they will perform, right? And what is the lifetime, etc. And therefore, we have all the observations, satellite observations, as well as the ground observations collected by the radio sound. So if we plot the profile of temperature and moisture in the troposphere collected by radiation, you will find many thin layers in the troposphere where there will be inversion, temperature inversion, right? But normally, by and large, the temperature will decrease with height. Okay. Then within the stratosphere, the vertical mixing is strongly inhibited by increase of temperature with height as in inversion layer. As I said earlier, within the stratosphere, because of the presence of the ozone which absorbs the UV radiation, temperature increases. Okay, with height in the ozonosphere, in ozone layer. A good example of inhibition of mixing is the formation of anvil shape created by the spreading of cloud tops generated by intense thunderstorms when they reach tropopause level. Okay. Have you seen a cumulonimbus cloud, full form cumulonimbus cloud? Something like this. Can you see this diagram? Is this diagram visible to all of you clearly?
Yes, sir, but it's so small.
Yes, sir.
Yeah, although small. But no, this is a diagram which shows a cumulonimbus cloud fully, full form, blown form, right? And what you see here is the anvil, the top of the cloud, top of the cumulonimbus cloud is spreading horizontally. Is not able to go further up. See, it spreads horizontally, right? There is a deep cumulonimbus cloud, and the top is spreading horizontally. It is not going to, further high because of the presence of the inversion, because it has almost reached the tropopause. So above that, the temperature is higher, increasing. So it cannot penetrate, right? So there is an angle here. And this is a very, very typical, not always you see this kind of standard cumulonimbus, very rare view. But most of the cumulonimbus have, the deep cumulonimbus clouds have, because generally what happens is when the cumulonimbus clouds forms above you, you will only see the base of the cloud. You can't see the top of the cloud, right? When the thunderstorm passing over you, you will only see the base of the cloud, right? You can't see the top of the cloud, isn't it? And so, since you can't see the top, so you miss this kind of scene, this vision you miss. It can be seen if you're flying through the aircraft, or if the cumulonimbus is very far away from you, then you can see this cloud. Okay. So, because of this inversion, it is not able to spread. The stratospheric air is extremely dry and ozone rich, that you know. The absorption of the solar radiation in the ultraviolet region of the spectrum by stratospheric ozone layer is critical to the habitability of the Earth. Okay, critical to the habitability of the Earth. Sorry. Okay. So, as you know, the ozone layer protects us from the dangerous UV radiation, right? And if it reduces, if it thins down, then we have a problem. Then you might have heard about the ozone hole, right? Ozone hole. Have you heard of the ozone hole? Yes or no? Ozone
Yes,
hole.
sir.
Yeah. Generally, ozone hole is formed or found on the polar regions. Now it is better. A few years ago, rather a few decades ago, it was a very, very dangerous situation. A very concern of the worrying situation, because the ozone was decreasing at the poles, and so there was a ozone hole through which UV radiation could penetrate to the earth, and which can damage our skin. You can get the skin cancer and so on. Right? So it is very, very important for the existence of life, right? A stratosphere. Heating due to the absorption of UV radiation by ozone molecules is responsible for the temperature maximum approximately at 50 kilometers that defines the stratopause. Okay. At 50 kilometers of the ground, the temperature is maximum in the stratosphere or at the stratopause because of the absorption by the ozone. So above that, as you have seen in the diagram earlier, you have got the mesosphere. Okay. mesosphere, in which the temperature decreases like the troposphere with height to a minimum that defines the mesopause. You have seen the diagram earlier. And in the thermosphere, temperature increases with height due to absorption of solar radiation, due to photodissociation and photoionization. Okay, in the thermosphere. So again, mesosphere is like a troposphere in terms of the rate of change of temperature with height, and thermosphere is like ozonosphere, like rate of change of temperature with height. Now we have got a mesospheric radar, MST radar, mesospheric stratospheric radar. We have got two such radars in the country. You know where they are? We have got two so-called MST radar, mesosphere, stratospheric, and tropospheric radar, MST radar. You know where they are located? Any idea? Where the
No, sir.
mesospheric? No? Okay. Well, one MST radar is located at Gadanki in Tirupati. You know Tirupati? In Andhra Pradesh.
Yes, sir.
Tirupati, there is a lab called
Yes, sir.
NARL, National Atmospheric Research Lab. It's a part of the ISRO lab. Okay, ISRO has a lab at Tirupati called NARL, National Atmospheric Research Lab. And NARL has a MST radar. That is a mesospheric, stratospheric, tropospheric radar, which can measure the profile of temperature and wind up to mesosphere. Right? Generally, as I said, the radiation can go only up to tropopause, or sometimes a little bit above tropopause. Above that, it can't go because it just will balloon will burst. But we have through radar, we can measure the profiles up to about mesosphere. We call it MST radar. So one is at Tirupati in Gadanki, and other is at Kochi in Kerala. Cochin University has got a project by DST, Department of Science and Technology of Government of India, which has funded that project. And through that project, Kochi University could install another MST radar, which is in Kochi, okay, which is funded by DST, the Government of India. So these two radars we have got, which measures the profiles of the temperature and wind up to about mesosphere, up to the top mesopause. Okay, in thermosphere, the temperature vary widely due to variations in the emission of UV and X-ray radiation from the sun's outer atmosphere. Okay, as we already said, that the temperature increases with height in the thermosphere. Okay, so these are the stratification of temperature or the variation of temperature in different layers of the atmosphere till about 100 kilometers. We don't go beyond 100 kilometers. In fact, for our purpose, we talk mostly about up to troposphere, right? For most of the models, we have up to tropopause. Of course, we consider the top of the atmosphere as sometimes 10 millibar also. It's quite high, about 50, 60 kilometer. 10 millibar is quite high. But the problem is the data. How to get the data on regular basis? Above tropopause, data is a big problem. Within the troposphere, no problem. There are so many sources of data. But above the tropopause, the data source is very less. Okay. So that is about the temperature. Now, how about the wind? We have got very little time. We'll try to finish this topic today. Okay. So winds. Let us see how the winds vary in the vertical, in the atmosphere. How the winds are formed. You know that. How the winds form, how the winds occur. It occurs because of the differential heating between low and high latitudes, which give rise to atmospheric motions on a wide range of scales. Right? The winds occur because of the temperature gradient, differential heating of the Earth's surface. Because of the differential heating, somewhere the pressure is high, somewhere the pressure is low, less. And then a pressure gradient develops, a pressure gradient force developed. So the winds from the high pressure area rushes toward the low pressure area, right? So this is how the winds form, winds blow, right? It's caused by the differential heating of the Earth's surface. They are called the atmospheric general circulation, which include planetary scale westerly tropospheric jet streams and lower mesospheric jet streams. Have you heard of the atmospheric general circulation? Atmospheric general circulation. Devasis, you might have studied. Have you studied general circulation of the atmosphere? Devasis?
Yes, sir.
Yeah,
Yes, sir.
yeah. General circulation of the atmosphere. Sometimes it is also taught in the geography class.
Yes, sir. We have studied it.
Yeah, exactly. So you might have studied. We have got like Hadley sail. That is a sail which occurs in the tropics because of the strong rising motion, because of strong heating in the tropics.
Yes, sir.
Hadley sail, and then we have got parallel sail. Then we got polar sail. We have got so-called hot latitude, etc. Subtropical high, right? Polar low, and so on. Polar high, subtropical low, etc. etc. Okay.
Doldrums, sir. Doldrums and ITCZ.
Latitudes and so on. So
Sir,
this
ITCZ.
the general circulation of the atmosphere occurs because of the temperature gradient due to the differential heating, okay, of the Earth's surface. Like at the equator, we have got strong heating, and at the polar region, we have got less heating. Right? So this differential heating causes the circulation. The air rises from the equator and eventually sinks at the pole, okay, and comes back toward the again equator, right? So there is a complete cycle, constant circulation. And you might have heard about as you go up, there are very strong winds in the atmosphere. At approximately 200 millibar or 150 millibar, there is about 12 kilometers or so above the ground. I've got a very, very strong wind. It can be about 200 kilometers per hour. Wind speed at that level, at that altitude, can be 200 kilometers per hour. Sometimes in extreme situation, it can be 300 kilometers per hour also. They're called jet streams. Have you heard of these jet streams? Yes or no? Jet streams.
No, sir.
No, okay. Jet streams you will study
Yes, sir.
later on. Yeah, later on in the classes, other classes also you will hear about jet streams. As you go up in the atmosphere, there is very strong winds, like about 200 kilometer per hour, approximately at 200 millibar, right? That is about 10 to 12 kilometers above the ground. And jet streams were just accidentally discovered first time during the World War. During the Second World War, we used to have very old type of aircraft, not like a modern aircraft of today. So when the fighter aircrafts were flying at that level, especially the Japanese aircraft, the American aircraft during the World War II, they were not able to balance themselves at that altitude because of the presence of very strong wind. And then they realized that there is something there, okay, and that they discovered it as a existence or presence of the jet streams, okay, which occurs because of the strong temperature gradient or thermal gradient. Okay, we will study more about this in some other course this semester, hopefully. So jet streams, okay, which are planetary scales. So this diagram illustrates the vertical distribution of wind field from 90-degree north to 90-degree south, plus minus 90 degrees. This is the equator. This is center. This is equator. Okay, this is the summer hemisphere. This is the winter hemisphere. Okay, so and this is the height in the y-axis. The height 0 kilometer, 10 kilometer, and so on up to 100 kilometers and so on. And this on the right side, you see the pressure 1000 millibar, 100 millibar, 10, 1, and so on. As you go up, pressure is decreasing, right? So this is how the average wind speed and direction looks like in the atmosphere. And you can see the troposphere is only very small layer, about 15 kilometer or 16 kilometer above the ground. If this is the ground, then this is the troposphere. Roughly, this is the troposphere, about 100 millibar. Above that, you have got a stratosphere. Above that, you have got mesosphere, and so on. So what you see is, in the winter hemisphere, you have got a very strong, this W indicates westerly wind. You know what is westerly means? What is the wind direction? When we say westerly wind, what is the direction of the wind?
Sir, west to east. West to east.
Exactly. Winds coming from the west is called westerly in meteorology. Okay. Whereas In the oceanography, it is just ulta, reverse. Wind coming from west, which is called easterly in oceanography for ocean circulation. When we talk about the ocean circulation, okay, then it's just convention is the reverse of the atmosphere. In atmosphere, we call the direction as the direction from which it is coming. Like if it is coming from the west, we call it westerly. And if it is coming from the east, we call it easterly wind. If it is coming from the north, we call it northerly. And it's coming from the south, we call it southerly, right? Easterly, westerly, northerly, southerly winds in the atmosphere. That's the convention. But in oceanography, we call the direction in which it is going. Like if it is going towards east, so we call circulation easterly. If it is going towards north, we call it circulation is northerly. So it's just reverse of the nomenclature or convention of the atmosphere. Right? So generally, these jet streams are very strong westerly wind. As you can see that W indicates westerly. They are all westerly, and these contour lines are indicating the speed of the wind. Speed is of the wind speed. So this bold line is zero. Bold line is zero contour. That means 0 meter per second. So you can just imagine. Now this is 10. This contour is 10. This is 20. This is 30. This is 40. 40 meter per second, right? Maximum. This is the average only. So maximum is 40 meter per second. So 40 meter per second wind speed is approximately how many kilometers per hour? 40 meter per second wind speed is approximately how many kilometers per hour? You can say quickly.
21.
No, 40 meter per second is approximately 4 times 160 kilometer per hour. 160 kilometer per hour approximately. You just convert meter per second into kilometer per hour. Now you will find it approximately 4 times. So 40 meter per second is approximately 40 into 4, about 160 kilometer per hour, roughly. Okay. So that's what I said in the beginning, that the jet streams have maximum wind speed of about 160 kilometer per hour, 200 kilometer per hour, in extreme cases 300 kilometer per hour also, right? So this is the wind speed, okay, in the troposphere in jet streams. And you can see that in the summer hemisphere, the wind speeds are less compared to the winter hemisphere. This is winter hemisphere, this is summer hemisphere. So in the winter hemisphere, wind speeds are stronger. Here it is only, this is 0, this is 10 kilometer per hour. So summer hemisphere, the speed is less. But as you go up, you can see that in the mesosphere, the wind speed is further high, so high. See, you just count the contours. This is 0, this is 10, 20, 30, right, 40, 50, approximately 50 meter per second. So 50 meter per second means approximately 200 kilometer per hour. Sometimes it can be even more than that. And also another thing you notice is that in the mesosphere, this is mesospheric region, right? Mesosphere, in the winter, the westerly wind is dominant throughout from surface up to almost like 100 kilometers. Throughout the atmosphere, in the winter hemisphere, the wind is westerly. Whereas in the summer hemisphere, you see that in the mesosphere, the wind is easterly. E means easterly. In the mesosphere. Again, if you go above that thermosphere, then it is again westerly. Okay, so this is the characteristics of the variation of the wind fill in the atmosphere from surface to the top, from the summer hemisphere to the winter hemisphere. Okay. The figure shows idealized meridional cross section. You know what is meridional? Meridional means in meteorology, this is
North south wind.
Yeah, exactly, north to south. When you say along the meridians of the earth, that is meridional wind. And we have got zonal wind, that means east to west, right, along the latitude, right. So the easterly and westerly are called zonal wind, and northerly and southerly are called the meridional wind. Okay, this figure shows a idealized meridional cross section of zonally average zonal wind meter per second around the time of these solstices. When the meridional temperature contrasts and winds are the strongest, control interval is about 10 meters per second. Zero control is bold. Okay. So very interesting variation of the wind with height in the two hemispheres. The winds in the tropospheric jet stream blow from west throughout the year. Okay, throughout the year is westerly. Jet streams are westerly. They are strongest during the winter and weakest during the summer. In contrast, the mesospheric jet streams undergo a seasonal reversal. Like in winter it is westerly, but in summer it is easterly. During the winter they blow from the west, and during the summer they blow from the east. Okay. Superimposed on tropospheric jet streams are eastward propagating baroclinic waves that feed upon and tend to limit the north-south temperature contrast across the latitude. Baroclinic, barotropic, you might not have heard about these terms. Baroclinic atmosphere, barotropic atmosphere. Have you heard about that? Not yet. Probably not yet. See, barotropic atmosphere we shall study later on, more in detail in dynamic meteorology also, dynamics of atmosphere. Also we shall study in physics, not much in physics, but mostly we will study that in dynamic meteorology or dynamics of atmosphere, or the baroclinic atmosphere, barotropic atmosphere. Actually, baroclinic atmosphere, you can say that the atmosphere in which the density is a function of both pressure and temperature is called a baroclinic atmosphere. But if the density is a function of pressure only, it's called a barotropic atmosphere. Okay, that is the definition of barotropic and baroclinic. When the density is a function of pressure only, it's called the barotropic. When the density is a function of both temperature and pressure, it's called baroclinic atmosphere. And most of the mid-latitude systems like extratropical cyclones, they are formed because of baroclinic waves. Okay. Generally, in tropics, the atmosphere is barotropic. I think we have already exceeded the time. We have to quickly finish. Just a few more minutes. Low-level flow in baroclinic waves is dominated by extratropical cyclones. Okay. Tropical cyclones, however, derive their energy not from the north-south temperature contrast, but from the release of latent heat of condensation of water vapor in deep convective clouds. Tropical cyclones form because of the convection, not because of the baroclinic waves. There are two tropical systems right now. You see the satellite picture currently. Today, there is one severe cyclonic storm in the Arabian Sea, and there is a deep depression, I think depression in the Bay of Bengal. You know that? If you just watch or see the satellite picture, you will find that there is a tropical cyclone currently in the Arabian Sea moving towards Somalia, and is already named. It's called Gati. That is the name of the cyclone given, Gati. Have you heard about that? Gati. Any of you? No?
Yes, sir.
Yeah.
Yes, sir.
Yeah. Good. Presently, there is a tropical cyclone in the Arabian Sea. It's named as Gati. It's moving towards Somalia, and one is forming in the Bay of Bengal, close to Sri Lanka, more southeast of Sri Lanka. Is likely to form into a cyclone, but presently it is in the form of a depression. Okay, just see the satellite picture. See the IMD website. You will find all those information. Okay, so those things you should see for your own up-to-date information. Okay, so we stop the class here today. Okay. Any question up to now? Any question?
No, sir.
Okay. So already we have exceeded the time. It's about almost like 1:45. So we have a lunch time now. So if there is no question, anybody else who joined the class later on whom I forgot to call the name in the beginning? Anybody who came late, who joined late in the class today? Just tell yourself, identify.
Yes, sir.
Devashish, okay, you joined a little bit late.
So Devashish.
Yeah, Devashish. Who else?
Yes, sir.
Bijit, yeah, I call your name. Anybody else? Okay, anyway, I have also now got the automatic attendance marker. So now after this class is over, immediately I will get a file which will indicate timestamp of everybody, all the students who came at what time and left at what time, got disconnected at what time. I have got a log of all that. But anyway, I want to ensure also that you are present, because sometimes people can log in and then they just go and do some other work. Therefore, I have to ensure that you are also present. So I just ask you to switch on your video because of that. Okay. So all right. So today we stop and then we'll continue this tomorrow. Okay.
Okay, sir.
Yeah. And
Yes, sir.
Yes, sir.
yeah. I stop recording. Stop recording.